Okay, so now we are going to start with another topic of our lecture notes, and this is internal energy. So now we have learned about temperature, we have learned about equations of state and work, mechanical work, expansive work. And now we're going to introduce internal energy, which is the third most important concept in thermodynamics. And okay, so the way we are going to do it is in the beginning we are going to define what is a function of state as opposed to variables of state. And that would allow us to define what process variables are as opposed to state variables. So then we are going to make an observation that comes from empirical from experiments, which is the fact that the work done in a thermodynamic process on a system which is adiabatically insulated is independent on which specific protocol you apply to the system. So what is the path that you choose to take from the initial state to the final state? That doesn't matter. You always end up doing the same work if the system is enclosed in an adiabatic container, and this adiabatic work is actually what we're going to call internal energy, and it is going to be a function of state. So then we are going to do a little discussion on the equivalence between heat and work and how it was realized that heat and work are two ways to exchange adiabatic work or internal energy, and we are going to be able to formulate the first law of thermodynamics, which is just an energy conservation law. Then we are going to introduce a series of coefficients, coefficient of thermal expansion, isothermal compression, molar heat capacity at constant pressure, and molar heat capacity at constant volume. So we're going to see what those are. And we're going to describe a historical experiment that will allow us to, so this is the Joule expansion, and this will allow us to write the internal energy of the ideal gas explicitly. And finally, we are just going to say what an adiabat is, and just like we did with the ideal gas in the case of the isotherms, we are going to write down the expression for the adiabats of the ideal gas. Okay, so let's just begin with the functions of state, and for that, just imagine that you have a thermodynamic system. So it could be anything. Just let me for a moment. Okay, here. So imagine you have any thermodynamic system you like. Let's call it sigma, and this is described by two independent variables of state, x and y. Okay, so now imagine you define any real valued function of x and y. So two variable function k x y, which is real valued. This system could be described by more variables of state which are independent, so we are not limited to the case of two. It's just for simplicity here of notation and everything that I'm considering only two. Okay, so I define this function, and this function is a function of state or state function. And why do I say this? Because you know that if you then represent the equilibrium states of the system, you would do it in the xy instead of the Vp representation, and any point here, which would be x and y, is a state of equilibrium. Yes. So if I give you a state of equilibrium of the system, then the function takes on some value. So the value of the function depends on the state you are in. Okay. So you can always write this in this form. So imagine you have two states, a and b, and you want to integrate the differential of this function, and you know by the fundamental theorem of calculus that this is k of b minus k of a. Okay, so again, what I'm saying is that the change in this function of state in between two different equilibrium states of the system is only given by the value of the function at the endpoints, but it's not given by which specific protocol or process you decide to go when you go from A to B. So imagine A is here and B is there. Okay, so then, well, it doesn't matter which path do you choose to make that integral, you will always get the same result. Okay, which is the k of b minus k of a. So it's independent of the path. That's the most important thing. And because this is the case, of course, you can always make a round trip. Okay, so you can, for instance, in this example I'm drawing here, you can choose to go from A to B using this path, and then come back using a different path. And because you know the integral doesn't care about which path you are choosing, you will get a 0 there. Okay, so just say the integral in a round trip of differential of k, which is a function of state, is just going to be the integral from A to B plus the integral from B to A, but this is of course equal to the integral from A to B minus the integral from A to B. So this is always going to be 0. Okay, so simply writing that for a given k, the integral over a round trip is equal to 0 is already telling you this is a function of state. So that's an equivalent way to state that k is a function of state. Okay, and sometimes you will see that they call this perfect differential. Okay, that's just notation. Sometimes maybe we use this term, so let's write it here just in case. Perfect differential. Okay, right. So now another, this is a side remark really, it's not necessary for what we are going to do just now, but it's going to be very important for us in the future. Again, you have your function of state of two variables, its real valued function, and provided that its second derivatives exist, the second partial derivatives of this two varied function are defined, then it is true that they commute. So this is the statement: the second derivative with respect to x and respect to y is the same thing as doing the second derivative of k with respect to y and then with respect to x. So it just says that the second derivatives, just taking the derivative with respect to x or taking the derivative with respect to y, commute with one another. And this is called Schwarz's theorem. Sorry. Maybe misspelled, Schwarz theorem for the mixed derivatives. There's several theorems due to Schwarz. This has consequences of practical interest for us, because in many cases in thermodynamics we are going to be writing the differential of a state function, and we are going to manage to write it in different ways, okay, depending on different choices of independent variables, for instance. So we know that in this case independent variables are x and y, but they could be something else. And we are always going to manage to write the differential as something times one independent variable, differential of one independent variable, plus something else times the differential of the other independent variable. And if there were more independent variables, well, there you go. You continue doing this. So what Schwarz's theorem tells us is that the partial of x with respect to y is equal to the partial of y with respect to x. Okay, that's just what is written there, because of the chain rule. When you want to write the differential of k, then you would say, okay, that's a partial of k with respect to x, differential of x, plus the partial of k with respect to y, differential of y. And then here you can identify this term with that term, and this term with that term. So just applying Schwarz's theorem, you see that the partial derivative of x with respect to y equals to the partial derivative of y with respect to x. Okay, so this is going to be really, really useful for us, especially when we start with the advanced thermodynamics part of the course. So don't forget about it. Okay, so then just rephrasing this condition, just because thermodynamic functions of state or thermodynamic properties, they are also called function of state of thermodynamic properties. These are linked to a quantifiable feature of the system. So it does make sense to say how much of k does this system have, okay? And this is not the case, for instance, for other variables, and we have only seen one, so this is not the case for work. Because you remember that when we finished the previous chapter, we saw that when you integrate the work done on the system over, for instance, any closed path, just like we are doing here, this was always going to be different from zero. It could be larger than zero or smaller than zero, depending on whether you go counterclockwise or clockwise. But the thing is that it's never zero as long as there is any area enclosed in the loop. So this is always going to be different from zero. So certainly work is not a variable of state. Actually, work is what we call a process variable, okay? Because the integral over a round trip is always different from zero, or yeah, it's always different from zero. So work is not a function of state, or state function, or thermodynamic property. All of these terms refer to the same thing. Function of state. State. Okay. So what work is what we call a process variable. Okay, so work is a process variable. Process variable. And this is opposed to state variables. So always keep this in mind. We will see at least one other more process variable and a lot more state variables in this course, in what is left. So okay, then I told you we were going to make this comment about the adiabatic work. Okay, so now again, imagine we're in this system, which is our usual piston setup. I'm going to make it adiabatically insulated, so let me just put a double layer here and make it a bit larger like this, so that you get a nice rectangle. Let me just do it a bit better. Okay, good. So we have an adiabatic insulation in a piston, and here we have the piston, an expansive system, sorry, and here we have the piston. Here we have the gas, but because of the adiabatic insulation, there's no chance that heat can come in or out, and then you do a protocol. Okay, so you want to go from the initial volume VA to final volume PV, whatever, just larger. Okay, and you do that quasi-statically. Let's say you do that quasi-statically, and you keep track of how much work did you have to do externally to achieve that. In that case, that would be work that the system is doing. So, for instance, you could think then of a different experiment in which you want to go compressing the gas, so that it's more intuitive for you, perhaps. So you are compressing the gas from volume A to volume B, okay? And you have to do some work on the system, and you maybe keep track of how much work you had to do for that, and you can do it quasi-statically. So let's just make a VP diagram of this. So this is the volume, this is the pressure, and you're going from one volume A, which is somewhere here, to one volume B, which is somewhere there. So this is A and this is B. You're compressing. And if you do it quasi-statically, well, this is what your process is going to be doing, and you can measure how much work did you have to do that, and you keep track of it. Okay, you just write it down. Now imagine you do a different quasi-static process, something like that. And surprisingly enough, you see that it takes the same amount of work to go from A to B, doing process 1 or process 2. And you can actually cook up some more exotic processes, and you will see the same thing. Actually, this is even the case if you do a non-quasi-static process. Okay, so if you go suddenly, if you go out of equilibrium, say, I don't know, or even if you do a mixture of the two. Imagine that you do quasi-static isobaric process represented by this horizontal line, and when you are here at the corner, maybe you do something sudden, okay? When you suddenly do something, so there will be some non-equilibrium dynamics, and eventually you will fall into the same final state B, and you find that also in that circumstance, the adiabatic work amounts to the same thing. So what I'm saying is that the integral from A to B of the adiabatic work, let's just write it like this, is always the same thing, regardless of the path. I don't have to specify a path in the integral, and I'm going to just give a new name to adiabatic work. I'm going to call it internal energy. Okay, and what I'm seeing in this statement about experimental evidence is that the integral from A to B, two equilibrium states, of this new thing is only depending on the endpoints, on what the endpoints are, and it's independent of the path. So this means that this thing I've just defined is a function of state, or is a state variable, or it's a thermodynamic property. Okay, so it's a new thermodynamic property of our system. Function, this is not spelled properly, function of state. Okay, so that's how we introduce the internal energy, and in particular this is the internal energy. Okay, so how do we define, because before I told you that functions of state are properties that it makes sense to state how much of that property the system has. And it doesn't make sense to say how much work a system has when it's in one state, but it does make sense to say how much internal energy it has. You can compare the internal energies of different equilibrium states of a system. And the way you do it is you can define some arbitrary state of the system, which is going to be a reference. I'm going to call it O. And this is an equilibrium state, some equilibrium state which is convenient for me. And any other state, say A, has an internal energy UA, which is defined by simply setting an adiabatic process that connects O with A and calculating how much adiabatic work I have to do in this process. Okay, and like I say, I can choose any process I like for this trip from O to A. Process could be quasi-static or non-quasi-static even. Okay, so I choose whatever process is convenient for me. And I just say that the internal energy in A equals the internal energy in the reference state, which I can give some referential value of my choice, which could in particular be 0 if I want. And then I calculate what is the adiabatic work going from 0 to A. I'm not writing it as an integral, because if I write it as an integral, it is assumed somehow that there's something quasi-static about it. Okay, so it's just some adiabatic work that just happens to take me from the reference state to any other state A. This additive constant is actually not a problem, because usually I'm going to be interested, or always actually, I'm going to be interested about changes in the internal energy and not the absolute value of the internal energy. And when you are talking about the change of internal energy when going from any state other than the reference to any other state, say from A to B, like we did a drawing here, then this is, of course, by the definition I just wrote, this is U of 0 plus the adiabatic work of going from 0 to B, and minus U of 0, so U of 0 goes with U of 0, minus the adiabatic work it takes to go from O to A, in this case, adiabatically. Okay, so in the end of the day, I really don't care about the constant, and always I will be interested only of the difference in internal energy between any two relevant equilibrium states of my system. Yeah, so then there are of course, this thing I can write it as the adiabatic work between A and B. Okay, this is what we saw in the very beginning when we introduced the definition of any function of state. So one important remark here is, well, actually two of them. One I told you already. So sometimes it may not be possible, and often actually is the case that it's not possible to go from one equilibrium state A to one equilibrium state B through a quasi-static adiabatic process. Okay, so there is an issue about adiabatic accessibility. In order to be able to define internal energy in this way, okay? Because I'm just saying that internal energy, which is a true thermodynamic physical property, I'm defining it in terms of the adiabatic work it takes to go from one equilibrium state to another. But of course, it must be possible to take adiabatically one system from one state to another. Because if it's not possible, then I should choose another definition, because there could be cases in which I cannot even define the internal energy of a state. So the whole thing is really subtle, but the only thing to remember is that, okay, it doesn't matter if it's not possible to go quasi-statically from initial state A to final state V, then you do a sudden and non-equilibrium process, and you can always do it like that. Again, there is another caveat to this, which is it may not be possible to go from A to B at all, not even through a non-equilibrium process, okay? But in those cases, it will always be possible to go from B to A. So don't worry about it, this one will always be possible. So then, what you have to do is, if you want to say what the difference in internal energy is from A to B, which is UB minus UA, because this is a process that you can't do, what you can do is to go from B to A, okay, adiabatically. And if you can do that, then you change the sign and you get the difference between the internal energy in B and the internal energy in A, okay? So it doesn't matter that you cannot go from A to B, you can go from B to A in an irreversible fashion and measure how much adiabatic work you need to invest, okay? So now the final comment of this first video would be that, okay, now imagine that our system, which is enclosed in this adiabatic, perfectly insulating walls, well, imagine that the walls are not so good insulators, okay? So imagine that there is a little bit of heat leakage through the walls, even if it's tiny, there is a little bit. So then what happens is that, well, the change in internal energy, okay, must not be exactly equal to the work. It must be something more, okay? So that something more, we are going to call it Q. Okay, so this is just a definition, really, okay? So whenever I have a system which is not perfectly thermally insulated, the change in internal energy, or in other words, the adiabatic work in going from one equilibrium state to another equilibrium state, is not entirely going to be due to whatever mechanical work I'm doing to the system, because there's always going to be something else, okay? But this, I can always define it, okay? If I want to know what this is, but then I put a proper adiabatic insulator in the system, and I do the process that takes me from the initial state to the final state. I measure the work, and I know what this is. The whole point is that if I do any other process which is not adiabatic, and I measure the work I do, I perceive that there is something missing to sum up to the total change in internal energy. And that something is going to be called heat, actually. So this is the point in the course where we are going to properly define heat. Okay, so this will be in the next little bit of video.